Great. It's my great pleasure to be here and talk about some of our recent research on open data and the robustness and reliability of empirical research built on organic data, in particular web data. So the focus of my talk is going to be about robustness and reliability of research results if such research results are built upon the analytics of organic data like the data on the web. My name is Nan Zhang. I am co-director of the Privacy Plus Analytics Lab at Penn State University. So before I start talking about the details of robustness and reliability of data analytics, let me first point out that in recent years, there has been more and more research that leverages a goldmine of data available on the web. So such data could include social media data. It could include, for example, Twitter, LinkedIn. All these social media expose large amounts of data on the web. It could include e-commerce data as well. Amazon and eBay has ranked lists of products they sell, has customer reviews, contains not only information about the prices of products, but also how customers feel about them. So all these data on the web, or more generally organic data, really form a gold mine of information for researchers to leverage. And the question is, when we leverage such data, how exactly do we ensure that the usage of web data is proper and unbiased? So when we leverage web data to form research findings, the research findings can be robust, can be reliable, and not based on biases that are either inherently in the web data or introduced during the data analytics process. So corresponding to the topic of this workshop, we can see that recently research on organic and web data in particular has appeared in a wide spectrum of research communities. Of course, computer science community has actually spent a lot of time investigating how exactly do we enable analytics over web and organic data sources. How do we enable proper data collection, sampling, analytics, mining, etc. Now, from the usage perspective, not from the technical development perspective, we see that web data has been used from sociology to psychology, from management to marketing. Many prestigious journals have published articles that use web and organic data sources as the basis of their data analytics and as the basis of forming their research findings. This represents a general workflow of how such empirical research usually proceeds. Note that this is not the only workflow possible, but it does capture the common steps in data analytics over web and organic data. Now, if we look at the general workflow that happens here, it is not that different from traditional research built on design data. Now, why exactly do we say that? Now, let me go over this workflow first. If we consider people in the real world as our population, the first step of this workflow is to sample from this population to form a sample that we will then use in our research. Now, in design experiment, the sample could be the human subjects that we recruit. In organic data sources, such sampling could be a random sample of social media users. It could be those people who post their reviews on e-commerce websites. But the general principle of the first step is we take a sample from the real-world population. The sampling process, well, ideally would be unbiased, given everyone the equal chance of being represented. In practice, there will be bias in this sampling process. We'll talk more about it later. But after we get sample, the next step is we design experiment or analysis over such sample in order to collect our data. Now, in traditional design experiment, what happens here is we would design an experiment, maybe put the human subjects into treatment groups and control groups, and then collect the data based on how they respond to the experiment design. In organic data sources, what happens here is we generally would capture the kind of information we would like to capture. if we want to measure people's emotional responses to certain incidents on social media, then we would collect their tweets and then extract the emotional signals we would like to capture from such data sources. The output of this step would be the data that we then go through statistical analysis like data mining or some alternative forms of data analytics operations in order to form our final research findings. So this is the general workflow. As you can see, it's really shared between the traditional design experiments and the relatively new organic data analysis. But another thing that I would like to point out here is even though this general workflow is shared between design data and organic data, the key challenges are totally different for the two kinds of data analysis workflows. As I said, for designed data, generally we would recruit human subjects in the sampling steps, and then we would design experiments according to the hypothesis that we would like to test. There has already been rich literature talking about what exactly are the potential biases that one could introduce in the subject recruitment step as well as in the experiment design step. Now, if we look at what happens with organic data analysis, data collection generally happens with these web data sources. Now, what happens is, for example, if we want to collect the user data from Twitter, then we would usually have to start with some Twitter users, look at their friends, their followers, etc., in order to form a larger pool of Twitter users that we would like to analyze later. In other words, form our sample. Now, if we are interested in tweets, then the sampling process generally involves issuing keyword queries to Twitter and then look at the return the results as our sample. Now, what happens here with these sampling steps is that there are some easy-to-use sampling methods. For example, snowball sampling has been pretty popular. A very intuitive idea would be if we randomly issue some keywords to a search engine or to a social media website and then take the results, and the results would form our sample. There are a lot of heuristics available, but there has been relatively little research on what exactly are the potential biases introduced by these sampling processes. If we follow the simple heuristics, then would we actually favor some samples over other samples? Would we actually oversampling part of the population and undersampling the others? So recently, my collaborators and I, we started some research on the bias analysis for data collection over web data, for example, and we found that the simple approaches, for example, randomly issuing keyword searches to get a sample of documents or a sample of tweets, etc., would introduce significant bias to the results. Instead, in order to correct these biases, you not only have to be aware of the existence of the biases, you also have to understand the statistics about the underlying corpus, the underlying population, that is, you are drawing samples from, and then you can design the proper sampling process in order to eliminate the bias. Now, I won't go into the technical details later, but in later part of this talk, I will show you some examples of what kind of biases could be introduced in the data collection process and what's the implications of such biases. Now, if we move forward to see what happens with the experiment design phase. Traditionally, experiment design is a focal of concerns. People have talked about how exactly biases could be introduced with flawed experiment design and whether research findings would be reliable or robust or not, depending on whether the experiment design is rigid or not. Similarly, a challenge we face with organic or web data analysis is the data processing step relies heavily. Data processing is now the experiment design, and it relies heavily on automated techniques that inherently would contain error. Many things we have seen so far in the data processing step. For example, like the example I gave, if we are interested in the emotional responses of people to certain incidents, then the data we collect would be the emotional signals we capture from social media. But how exactly do we capture such signal? Because of the vast volume of data involved in this case, we have to rely on some automated techniques to extract the emotional signal from the unstructured text data. And this step, even though the technical community has put in a lot of efforts on developing natural language processing techniques, information extraction techniques, entity resolution techniques, all these techniques would inherently contain error. That is, it wouldn't give you 100% accuracy when you try to, for example, extract location from data, extract names from the data, or just to determine whether this particular text, this document, is related to the topic that you are interested in. Now, generally, we accept such error as a trade-off that we pay when we automate the data processing or the experiment design phase. But on the other hand, it is important to understand, let's say if the error rate is 5% or 10%, then would this 5% or 10% error rate affect the validity of your final research finding? Especially when you have a pipeline of data analysis going on in the experiment design, then how exactly do these errors actually combine with each other? How do they get composed during the data analysis workflow? And whether the end result, the research findings you get from the experiment design, would still remain valid given all the potential errors of the data processing workflow that you adopt. So this is the second step, and again, it places significant challenges on understanding the potential biases, the potential issues introduced in the data analysis workflow, and we don't have enough results to enlighten us on whether significant biases would be introduced by this step. And finally, I would say both traditional design data and the relatively new organic data would face similar challenges on the last step, which is statistical analysis. For example, recently political scientists have talked about the issue with extreme counterfacts, which essentially means that to which extent can we use the statistical models we build to predict future events? In which cases would the prediction be so far-fetched that it depends more on the model you use rather than the original data you use as your evidence? Similarly, when analyzing organic data, we would face exactly the same kind of challenges in statistical analysis. Now, if we look at the differences between organic data and design data, I would argue that the organic data and design data, when we look at the potential biases, they are quite different in what kind of biases is understood by the community and what kind of biases is most dangerous to the validity of research findings. In particular, as I said, the traditional research on design data has already established well-designed principles on methodological scrutiny over the design of experiments and over, let's say, the recruitment of subjects. We know what kind of biases could be introduced, and people have established the rules on how to avoid such biases. Very little work, however, on methodological scrutiny over organic data analysis. We don't really know where are all the places that biases could be introduced, and it's very difficult to understand what exactly could be the sources of bias that affect the reliability of the final research findings. Now, this difference in terms of whether methodological scrutiny has been properly established or not actually leads to different challenges on ensuring the robustness of research findings. I guess a lot of us have heard about this reproducibility crisis in psychology. But think about why in psychology people call for reproducibility as the main issue in ensuring the robustness of research findings. It's actually because they have a well-established methodological scrutinization process. They understand what kind of methodology are acceptable and which are not. So the main challenge there is whether the researcher would report the methodology they have used in a complete and comprehensive way that his or her peers can then judge whether the methodology made sense and correspondingly reproduce the research study. Exactly because the methodological judgments have been established that we are looking at reproducibility as the major challenge. But think about organic data. Is reproducibility actually the main challenge here? I mean, even if someone, let's say, report exactly what are the data analysis steps used in the study and exactly the parameters used in this study. Let's look at a concrete example. Let's say a lot of organic data analysis on Twitter data, for example, uses some data filtering steps. Like I will remove all tweets shorter than 5 words because it doesn't contain enough information for my analysis. Let's say a researcher precisely report the exact parameters, like in this case 5, used in the data analysis workflow. If you repeat this workflow, you can exactly reproduce what the researcher would get at the end. But what happens if I tell you that when we change this 5 to 4, that is to remove all tweets fewer than 4 words rather than 5, the research finding no longer holds? And the conclusion here is, even though the research study itself is reproducible, it is not really reliable or robust, because even though the researcher could have reported the exact methodology, the exact workflow used in the organic data analysis, because we don't have enough knowledge about what is acceptable and what is not in this workflow, we cannot judge whether the result is reliable or not. That's why we believe the main concern for organic data is not about under-reporting. Even if you report everything you have used, it's still not enough for us to understand whether the result is reliable or not, because we don't know the implications of changing some parameters on the validity of the final finding. So we believe the main concern here is actually the under-scrutiny of these workflows we use in processing organic data. And as a result of that, we believe, unlike design data, where the challenge seems to be on reproducibility, and therefore there have been a lot of calls on open data to address it. Well, in this case of organic data analysis, the robustness of the workflow, the robustness of the data processing steps seems to be the major challenge. And just to show you a few examples of that, I will just take a few special cases of what could happen in the sampling step, in the experiment step, and the analysis step. So I will use concrete examples containing workflows that have been used in papers published in the prestigious journals I mentioned a few slides back. But this is not about individual studies. This is really about looking at potential biases introduced by these commonly used data analysis steps, and then see what's the implications of these potential biases introduced by these steps. So the first is about sampling. And the bias that I will talk about here is really about the myriad set of confounding factors that could determine people's online behavior and captured in such organic data analysis, and yet not properly understood by the research community. And in order to demonstrate that, I would like to look at a very simple and intuitive way of looking at social media connections. Again, this methodology or this heuristic have been used in more than one paper, in multiple papers before. And the idea, if you think about it, looks quite reasonable. And the idea is this: if we look at the followers of 2 accounts on Twitter, you can replace Twitter with any social media website, follower with friends and favorites, and so on. The idea remains the same. If 2 accounts, when you compare their followers list, they have a large number of common followers, it means that the 2 accounts are similar. You know, they could be advocating for the same issue, they could reflect the similar brand images, and so on. So you've seen previous studies that actually measure, let's say, all the car mates, and then look at the percentage of common followers they have with, let's say, those accounts that advocate for environmental friendliness, for some other values, and then look at what exactly are the brand images of these termates in terms of different values advocated by the different Twitter accounts. It looks very reasonable until you actually look at what exactly are the confounding variables here that could potentially determine the number of common followers of different Twitter accounts. This is just one example. If you look at the percentage of common followers between, let's say, the eco-friendliness or the environmental advocacy groups and the different termates, now you can rank the termates according to the percentage of common followers they have with these eco-advocacy groups. But you will find some interesting outcomes. That is, usually when you look at the number of common followers, you would assume that a large number of common followers between two accounts are due to common interests. But what we have found is it depends on many other factors as well. For example, when we look at the previous paper that actually ranked termates and according to their common followers with these environmental advocacy groups, we found that the American termates seem to be ranked higher than those termates that are popular in other parts of the world. And we asked why. And we looked at the configuration there, and it seems that, well, a lot of the environmental advocacy groups used in the study are based in the US. So the higher number of common followers could simply be an artifact of both the termate and the advocacy group are based in the same country rather than they share the same value. So for example, we looked at EPA research, which is certainly an environmental friendly group in the US, and EU's environmental friendly advocacy group. And we look at how exactly would you have ranked the two termates, Rolls-Royce and Cadillac, based on the percentage of common followers with these two different accounts. And sure enough, if you look at them, the results are quite different. According to the European environmental friendliness group, you would say Rolls-Royce is more environmentally friendly. On the other hand, if you look at EPA research, you would say Cadillac is more environmental friendly. But the fundamental reason here is not about which brand is more environmentally friendly. In fact, neither of them has as strong a reputation here as, say, Tesla. But rather, it's because if you look at the percentage of followers for the two accounts, they are very different from each other. EPA research has a much higher percentage of followers from North America, and the EU environmental friendly group has a much larger percentage of followers from Europe. And I just want to show you with a system that we have built that this issue is by no means an isolated incident. And one particular example here is just to look at the two accounts. This is the platform we used, so we built so you could actually compare the statistics of the followers of different accounts. So I put up here the comparison between the followers of two BMW Twitter accounts. One is BMW USA, the other is BMW Motorsports. So you can say that if you try to measure the brand image of BMW, it's very difficult to distinguish between these two because, well, they both belong to the same company. But if you actually look at their follower distribution, it's quite different. And just some example, as I said, the country distribution could be quite different. By the way, we inferred country, in the case here is more like continent based on the time zones the users are in. In this case, BMW USA certainly has a larger percentage of followers from North America. If you look at the language distribution, it's also different. English language has a larger percentage of representation in BMW USA than BMW Motorsports, a more global brand, global account of BMW. Also, if you look at when a follower joined Twitter, the distribution is also quite different. for BMW USA, the distribution of its followers, the date its followers joined Twitter, peaked in around 2012 and then dropped and then peaked again in 2015. On the other hand, the BMW Motorsports account has its follower peaked around 2014, 2015. So what does it mean? I mean, think about users' common behavior on Twitter. Usually when they first joined Twitter, they are more enthusiastic about trying out things, about following different users, and so on and so forth. So if an account happens to be created around the same time a user joins Twitter, or let's say there happens to be some media buzz about a Twitter account when a user first joined Twitter, then the user would be more likely to follow that account than in other cases. So all these potentially confounding factors could affect a user's decision on whether to follow an account or not. And because following an account is not about actively participating in discussions which require constant efforts from the user, but rather is done once and forget about it kind of a thing, it's very difficult to isolate a user's intention on why to follow a particular account from all the potential confounding factors as I have seen here. And you can see that different car mates have very different distributions in terms of country, in terms of creation date, in terms of their followers' activities. And if you look at fashion brands and so on, you see these differences everywhere. So the point of demonstrating these differences is to say that it is easy to resort to a heuristic when we analyze Twitter data to say that when a user follows an account, it indicates some interests in the value advocated by that account or the business the account is in. When we actually want to form a research conclusion that is robust, however, we would have to test against all these potential confounding factors in order to ensure that, for example, the order of car mates that we get indeed reflect whether the brand image is related to environmental friendliness, or rather the rank is just an artifact of the different country distributions of an account's Twitter followers. So this is the first example about the many confounding variables we have to deal with when we look at sample collection on online social media websites. Now the second thing I want to talk about is about experiment design. And a uniqueness of organic data or web data analysis here in terms of experiment design is what I would like to call as a highly unbalanced cost structure. What exactly do I mean by that? Let's take a look at a traditional research study. In traditional research study, you recruit human subjects and then you randomly partition them into treatment groups and control groups. The recruitment cost you have is really the same across the treatment group and control group. In online social media, however, oftentimes treatment groups can be much more expensive than control groups if the only thing you are capturing from these subjects are their online activities. Because there are numerous potential users that you can put into a control group and then passively observe what they do without any intervention from you. One specific example, there was a study which actually looks at the effects of, let's say, gifting users in the treatment group with special access to, let's say, some premium subscription of a subscription-based service, the effect of that on the friends of the treatment group. Now, if you consider a experiment like that on online social media, the treatment group is expensive because you have to gift them with this subscription. It could cost you, a couple dollars, maybe $10 per user. On the other hand, control groups are free. You can put any number of users as your control group because you don't really do anything with the control group. You can just take any subset of the social media user and then observe their behavior. This extremely unbalanced cost structure actually leads to some interesting choices on statistical analysis. For example, what we have seen in some studies is that because control groups are so cheap and treatment groups are so expensive, it's very difficult to get a large treatment group or to repeat this experiment many times. Instead, an idea used in, again, several research articles before is, well, let's only have one treatment group, but let's test numerous, millions of even, control groups and see whether there is a statistical difference between the treatment group and control group. The idea seems very intuitive and straightforward. Let's say if we have tested 10,000 control groups, and we found that compared with the treatment group, let's say only 10 actually would, let's say, lead to a higher revenue from the subscription-based service perspective than the treatment group, then we would say the treatment is effective. Right? Because it outperforms 9,990 out of 10,000 control groups. The idea seems pretty intuitive. But if you actually look at the assumptions made by such a methodology, you will find some interesting problems that may not actually lead to a reliable research finding. So think about the logic behind this kind of an argument, right? This kind of an argument is to say that we would like to test whether the treatment group and control group are statistically distinguishable or not. If they were not statistically distinguishable, okay, they are statistically indistinguishable, then what happens is that, well, the treatment group is just one random variable generated according to this distribution, and because we test 1 million control groups, the control groups would be randomly distributed according to the same distribution. So roughly speaking, what we should see is maybe 50% of the treatment group would outperform a randomly generated 50% of the control group would outperform a randomly generated treatment group and vice versa. If we actually find that just, let's say, 0.1% of the control group outperform the treatment group, well, then that's great news, because that means it's very unlikely that we get to this finding with a randomly generated treatment group. It must mean there's something different about the treatment group so that it outperforms 99.9% of the control groups. The logic seems intuitive until you think about a tacit assumption made in this method. And the difference can be simply illustrated with this figure. In the previous figure, we made a tacit assumption that the treatment and control group actually are generated according to the same distribution. In this case, they are from different distributions. And let's consider an extreme case scenario where the treatment group has 50% chance to take the max value in the range and 50% chance to take the mean value in the range. And then what are you going to see? What you're going to see when you have one treatment group and then test 1 million control group is the following simple observation. If your treatment group happens to be the max value, you see that 100% of the control group would underperform that treatment group. So you will incorrectly conclude that, well, there must be statistical difference. Statistical difference there might be, but you will incorrectly conclude that the treatment statistically would outperform the control group. While what actually happens is you didn't see, with another 50% chance, you would have 100% of the control groups outperforming the treatment group. This is basically the flaw of using one treatment group but numerous control groups in order to leverage the low cost of control groups in this web data analytics scenario. You simply cannot conclude on whether treatment would statistically outperform control based on just one treatment group and no knowledge of the statistical differences in terms of distribution differences between the treatment and control groups. So we actually looked at, of course, this scenario is very artificial, but we did look at one real case used in an existing paper, and this is the CDF function we actually got on how much percentage of randomly generated control groups would outperform a treatment group. So you can see what happens. It's kind of similar to the previous figure I illustrated to you. Right? You have a fairly high chance, 20% chance, that all the control groups would outperform the treatment group. So you fail, you lose to all the control groups. You also have a fairly large probability, about 30% probability, that none of the control groups would outperform the treatment group. And everything in the middle are the other probabilities that you are going to see. But what happens here if you use that methodology of one treatment and numerous control group is there would be 30% chance for you to conclude that your treatment outperform almost all control groups, and therefore there must be a statistical superiority of your treatment over control, which is wrong, because if you look at what happens here, they are really statistically, you can't make any conclusion about who outperforms whom. And just to give you a kind of illustration of the complexity of this problem, here is a demonstration that we built for different kind of graph topologies. And you can see, I don't have time to go into details, but one key reason why you see such a kind of extreme CDF function is because in the real world, these social networks, if you consider degree, for example, it follows the so-called power law distribution, which means there are some users that are that have numerous followers, while the vast majority of users have only a few followers. So there are these, you can say, very important users. And in many cases, if you hit some of these users in your treatment group, then you are kind of at the top right corner, and you outperform almost all the control groups. And on the other hand, if you don't hit any of them, you're on the bottom left corner. So this kind of power law distribution is one reason why you see these extreme CDF functions. And sure enough, if you actually test the different kind of graph topologies, you see that the CDF function depends a lot on the graph topology. For a fairly kind of uniformly distributed degrees, you don't see a very extreme kind of CDF function. Like in these cases, you can see it's not really that different from what you would kind of assume when treatment and control share the same distribution. But look at this one. This one is actually where you see the CDF function begins to deviate significantly from this straight line from 0, 0 to 1, 1. And this is a power law distribution. So if you look at some others, for example, this one. This one you can see a few nodes on the right corner has a lot of connections, while the others have very few connections. The CDF function is very different from what you would assume, and incorrectly conclude if you simply look at how much percentage of control groups would outperform the treatment group. So this is the second issue I would like to talk about today, which is the unbalanced cost structure and the problem with leveraging it to use just one treatment group and numerous control groups. The last issue I want to talk about today is actually the simplest issue, because I believe this is an issue that all of us understand, that the automated data processing techniques we use are not perfect. And as a result of that, if we just blindly use them, there are some unexpected consequences. For example, we have seen in many papers actually that try to determine the location of a tweet based on whether the tweet would include in its text the name of the city of interest. So examples of such studies would look at the city name mentioned in a tweet and then try to determine the distance between the location of the Twitter user and the incident being discussed, and see, for example, how distance would affect one's emotional response to the incident. These are published papers. But then, if you actually look at how exactly the accuracy of such keyword match plays out on predicting or determining the location of a tweet, you would find some actually quite surprising results. For example, here, we actually compared different methods to extract the location from a tweet. You can see 4 different methods here. Twitter match, which means that you give Twitter the city name and then Twitter returns to you all the tweets. This is the Twitter way of matching a tweet with the name of a city. And then on top of that, we can say that some tweets returned do not exactly have this city name in it. So we can do another round of manual filtering, that is the keyword match. And in some cases, we have city name containing multiple words like Los Angeles, so we can do a whole word match. That's the third way of doing this. And finally, we can use state-of-the-art NLP technique to do an entity resolution to see whether this word actually refers to a location or not. So if I could bring your attention to the first feature here, you can see some interesting results. This is basically depicting how much percentage of those tweets that Twitter believes match the name of a city actually refers to a location according to a state-of-the-art NLP algorithm. And there are 2 interesting findings here. One is different cities have quite different percentage. For Houston, for example, the percentage would be as low as 30%. For Chicago, it could be as high as 75%. Why? Because, well, Houston could refer to a city name. It could refer to a last name, like Whitney Houston. It could refer to a lot of different meanings. If you look at Phoenix, the percentage would be even lower. And on the other hand, another observation from here is that the percentage actually varies significantly over time. So it doesn't really stay stable from day to day. Just so you can see, for example, if you compare Phoenix is even lower. Why? Because Phoenix has even more meanings than Houston. It could be a bird, and it could be the name in movies, a name in books, etc., etc. So it's very difficult to know, if you just use keyword matching, how much of them actually reflect what you believe these keywords to reflect. This is actually a result we got last year when we ran it last summer. And you can see here that initially we were actually quite shocked to see that Houston's results is below 20%. So we actually tracked this over time, and you can see I won't go into details here, but the lines are actually representing the percentage of mentionings of Houston actually corresponding to the location of Houston, Texas. You see that in the beginning of August, there was a sharp drop of that percentage. And if you're wondering why, well, that day was supposed to be the birthday of Whitney Houston. So a lot of tweets were not about the location, but about the singer. So this is the third issue I want to mention. So even if you have addressed the biases issues in sampling and in the experiment design, in data analysis, you still have to pay attention to the automated techniques that you use so that you can understand the implications of it. So I won't go into details on some of the ideas we propose to address or alleviate some of these issues, because we have another talk to the day after tomorrow where we will go into details of these suggestions. But what I hope is just to show you through these system demos that no matter if you're doing sampling, where you have to be aware of the confounding factors, or if you want to leverage the unbalanced cost structure between treatment and control groups, or if you're doing data analysis, there are these subtle issues or nuances in the organic data analysis that we are not used to deal with in the traditional designed experiment. And they must be properly taken care of in order for the research results to be robust and reliable. So that's the conclusion of my talk today. Thank you.